I'll be talking a bit about problem definition issues in target leaks. And it's going to be a bit different, more statistics, more about bad science. So my name is Meir Maor. I work at Spark Beyond. We have an AI power platform to help data scientists find insights in their data. And I won't be talking too much about that. I will be discussing various things we've done. So I will be discussing problems we've seen with various customers in the problem definition and how they set up the problem, that they do stuff wrong. We'll start with stuff which I assume many of you are relatively familiar with, like target leaks, discuss campaign biases and various issues. We'll see how people get this wrong, how we might hope to somehow do something better and make this an easier problem to tackle. So just by show of hands, how many people are familiar with the term target leak? Okay. How many people never raise their hand? Okay. So a target leak, I'll define it. This is when we use information which is not actually available at prediction time. We cheat. We use the future. We want to predict the future, but we are using the future in order to predict it, or we are using something which is affected by it. So we want to predict our revenue for next month, but we will use, if we won't use our revenue, we will use something which is based on it or affected by it, like we would use our market share for next month in order to predict our revenue for next month, which this is not something we actually know. In an analytic scenario, when I'm taking back data, obviously I can have all this information, so it's very easy to accidentally use something which you don't actually have. So when you're creating your data for predicting, you want to train, you want to make sure you're using the exact same data which will be available later for the real-time phase when you want to actually make decisions, drive actions for the business, whatever that action may be. So, simple. Write your online phase, see what fields are actually available, use only those variables which you actually have for the on-time phase, filter them out, select those for your training set, only use those in the model. Should be easy. Well, not so much. So we'll do what I'm going to do throughout all this talk, and we'll be using a real example. So we have a customer, a very large online retailer in the business of selling online, shipping it out, and they have a whole slew of predictive problems. For example, they're interested in knowing who's going to order, how much they're going to order, categorizing the various users, the visitors to their website. And obviously there's a big difference between those who have already ordered and are obviously more likely to repeat, and those who have never ordered at all. So we, since these two types of users behave very differently, we normally model them separately. And we want to use all kinds of information. And we have lots of information about the user. We know what kind of browser he uses. We know various stuff he gave us in the sign up. We have some partial maybe demographics information about them. We have lots of stuff we can use in order to figure out who's going to buy. Now, one of the fields the user can fill in when he signs up to the website, he can fill in a shipping address, that's the purpose of the site. And obviously, this is very valuable information for all sorts of problems. It tells us where he lives. It can tell us what kind. Is it an upscale neighborhood, maybe? A lot of things could be relevant. We can have all kinds of information. Is there an apartment number, maybe? Maybe that's relevant. So a lot of things which we might want to possibly extract from the address. And it's a field on the sign-up form, so it should be available for any signed-in user. So we should be able to use it. And then we notice we have a problem. We notice that for all of the people who have made a purchase, we have an address, while we don't have an address for all of the people who did not make a purchase. So though we verified we have access to this field at prediction time, we don't necessarily have access to its final value. Now, the vast majority of businesses do not run a temporal database. It is not feasible when I'm offline trying to train a model to get a snapshot in time. What did this record look like at this point in time? If you're running a temporal database, then you're in luck. Then you can ask yourself, I'm making a prediction for this user's what was available for this user at this time point. But for the 99% of us who do not have a temporal database, which is pretty much anybody outside of the medical domain probably, and you cannot ask on an individual record level what it looked like at an individual point in time, then you have a problem. And though you may have the address for some users, you do not know which users you had this address for, so essentially it's not usable. You don't know enough about this field in order for it to be usable in a prediction in a way which does not leak the information that if the user later on ordered, and you'll have information leaking in from the future back into your model into the past. Now, how do we capture this? How do we capture this? Now, if we took the data as is, and we used the standard, we took the address field, and we did the basic. It's a text field. Okay, what will we do with text fields? We do TF-IDF, we look for word occurrences. So the leak will affect the model, but nothing will pop up. No top token will show with 100% recall and give us a hint that we have a problem. If we do zip codes, if we do geolocation, we'll get information which is partly related to the leak, and with a proper model and ensemble, it will be able to exploit this information and give us a very high recall. But with all of these types of features, we won't see anything pop out to us. Even if we look at the features, even if we inspect the model and we see that the word street correlates as a popular token, and we see the word street popular token, so that's not going to tell us anything. It's not going to hint that we have an issue. If we look at the basic feature, which is not a standard feature, take it address length or address non-empty, then all of a sudden it becomes easy. Once you have this feature in your feature engineering, and once you have a report of the importance and how they affect, and what's the predictive power as far as recall and precision of the address non-empty feature, the problem becomes easy. You see, it has 100% recall on those who will make a purchase, and that should immediately ring bells. Anybody who sees 100% recall with something far from zero precision should should know something is very wrong here and go investigate. So we see, just from this example, that with two things, by by having the correct feature, which utilizes the point to its fullest, utilize the leak to its fullest, and by looking at them, by looking at the data, looking at the, not using the model as a black box, but inspecting how it's used, what are the key drivers, this can easily flag to us issues in the problem definition phase. We'll take a different example, something slightly more interesting. We have a client who is in the mining business. They're looking for a mineral. I'm not going to give any details, so we're going to call it unobtainium. So they're mining for unobtainium in Never Never Land. And there are areas which they have deposits, which were explored, and they have deposits. And we don't really have true negatives, but we know unobtainium. It's unobtainium. It's very, very rare. So we're going to assume where we don't have deposit, it's very likely to be a negative result. So, and we want to drive future exploration. We want to cut down on our exploration costs and explore in the most likely ways to go about it. So how did we do it? So we take a very simple approach. We put a grid over the Never Never Lands, and we mark those with known deposits as positives, and we take the others as negatives, and we put in lots and lots of context, and in order to look for features, we look at the imaging, magnetic, radiometric, anything we've got, we throw it at it, and we try to find what correlates with unobtainium deposits. And we get out an amazing model, 99% AUC. We're all going to be rich mining for unobtainium. Except then we go and we look at the model a bit more specifically, and we notice we're actually detecting big holes in the topographic imagery where there are already mines, and we're not actually finding it. So that's a simple target leak. The topographic data shows you the mines, which are an outcome of the deposits, but it only detects known deposits. That's not terribly useful, detecting the known deposits. So let's go back. We'll find the stuff older. We'll remove the target leak, and we'll try again. We're still 96% AUC. We're still going to be rich. But then again, we go and we look, what are we actually doing? And we're actually noticing distances from roads. Now, not only do all mines have roads to it, even if we take the old maps of the roads, and we don't take information from the future about known deposits, we noticed this is where they were exploring. So we're actually, since not all areas were explored, and we're not interested in checking the explored areas, we're interested in the unexplored areas. So we have a problem where we do not have information about where data was explored or wasn't explored, and in order for there to be a known deposit, it's not a single instance. Our training data is not exactly what we're looking for. And this is a problem which we'll actually repeat. In order for there to be a known deposit, there needs to be a deposit, but someone also needs to have looked for it. So, in essence, instead of predicting where there will be a deposit, we're categorizing where people in the past have looked for deposits, which is a much easier problem, and that's what we do. Now, the obvious thing is, okay, let's remove the road data. Let's not look at roads. But that's not going to solve the problem. When we remove the road data, we're just asking to find the same phenomena from a different source. The same phenomena of, instead of predicting where the deposits are, we're predicting where people have looked for deposits in the past and categorizing what has been done. So by removing data, we don't solve the problem. And if there's one takeaway from this is it. We chose our negatives and our positives in this example from a different population. The negatives are reasonably all over the place. Then the negatives, we chose just assuming any sample we will take is likely to be negative. But the positives are an intersection of where we explore and where we look. If we take the negatives also only from the explored area, we can use anything we like. We can use roads, we can use magnetic, we can use topographic. We don't have to worry about what sources we have. If we just remove the roads, we're just asking for a weaker version of the same feature to pop up from something which still encodes the same phenomena which we're not interested in. And instead of killing off the features we don't like one by one until the leak is still there but spread out into so many features we can't actually understand it, the only real solution is to correct the sampling bias, is to sample from a reasonable distribution which represents the problem you want to solve. We'll take another example. We have early detection of cancer. So we have lots of patient data. We have their history. We have lots of routine tests, which they do. And we want to figure out who's at high risk for cancer or for some other phenomena, something else. So yet again, we'll take a straightforward modeling approach. We'll want to predict a few months, a few years in advance, depends on the problem, before the discovery. So we take the cancer patients, the positives, and we know when they were diagnosed. We'll take a few months back and look up to that point in order to prevent looking in the future. We know that's bad. So we want to look only up to a few months before, or a few years before, as the case may be. And for healthy people, well, they don't have cancer, they don't have a diagnosis date, so let's just put them all on one fixed date in the middle, more or less in the middle, and we don't want them to be used as the dates. We know if we give a fixed date for all of them, then that would be a feature, so we'll remove all the date information. We'll just use relative timestamps. Now, if you just listen to my previous slide, bells should be going off in your head. We knew there was an issue, and we solved it by removing the date information. Now, this doesn't actually work, removing the date information. If we take medical samples without the date information, just relative times, but all the negatives were from a specific time frame in the middle, and all the positives were spread out. Some of them were, say, 2010, and some of them were 2012, but all of the negatives were 2011. Then instead of predicting cancer, we will be solving the much easier task of finding differences in how medical tests were performed over time. And if you have multiple things, your machine learning model will always solve the easier problem. So if you're merging two problems again, then it will solve the easier problem. So, and the root cause is, you see, we knew this problem was an issue. We knew we did it differently, that's why we removed the dates. So when you're trying to remove information in order to prevent a problem of analysis, this is immediately should be a red flag. Why do I have to remove dates? Dates is well known, I know when the sample was taken. Once somebody tries, I want to hide it in order to prevent some sort of leak, you should worry, are you really preventing the leak or only removing the most easiest way to utilize it and still leaving many other smaller ways to find the same problem? So then let's try to think, how do we solve this correctly? And it's not that easy to solve this correctly. We can take a quarterly snapshot, and we take a quarterly snapshot every quarter, and we'll say who is going to be sick in so much time in the future for a label. But then we have a problem. The patients don't get cancer many, many times randomly. So if we have the same patient and we use the same patient in multiple quarterly snapshots, and then we have a problem, especially if we use the future as test, but we also use the same patient as trained in the past. If we let the same patient repeat, then we have a problem. And we also have correlated samples in the train, even if we have a really held out test set, but we have the same tested for multiple quarters, which we looked at, then the training set samples will be correlated. If you didn't have cancer last quarter, you're not going to have cancer today. If you did have cancer last quarter, you most definitely will have cancer today. This is not an impossible problem, but obviously having strongly correlated training samples makes it much harder to learn almost any machine learning model. So you can remove the duplicates and say, I'm going to use each patient only once. Now, if you randomly select a quarter for each patient to be used in, then you're fine. You still have the natural distribution of the data. But then you randomly select for many of your cancer patients a quarter which is too far back from before they had cancer, and then you lose a whole lot of positive samples. And sadly, for the data scientist perspective, good for society, we don't have quite as much cancer as we would like for machine learning. So just throwing out positive samples, that's not a terribly good idea. So we see we have a bunch of options which aren't terribly good. What we ended up doing in this case is sampling, assigning negative dates and according to the distribution of the positive dates. So each negative samples, we gave them a pseudo-cancer discovery date where the cancer was not discovered, and we assigned those from the same distribution of the actual cancer discoveries, which is close to uniform but not quite. And that seems to work, and then we use a totally separate held out just in case that system still creates a sampling bias in order to validate. So we have several types of flaws in how we see the information, how we set up the problem, how we select the sample population, what data we allow in. With the appropriate feature, it's fairly easy to see the problem. But you need two things. You need to have the appropriate feature, and if you have a magic box which generates features for you, well, that's going to be excellent. And more importantly, you need to actually look at them. Because if you're throwing in the data into your magic machine learning box and not looking at the insights, not looking at the patterns, then you're not going to know it. And unlike mistakes which have you create a poor model, these are actually mistakes which have your evaluation show you have an outstanding model. So they're very hard to catch, and people can go onto production with a model which is horribly, horribly wrong. And the evaluation on the back data said it's going to be great, and then hopefully they test the performance on an ongoing basis. And after going in production, depending on the pace, it can be a day into production or it can be a month. When the data starts coming in, then people say, well, that's not what we expected. And that all has to do with expecting the magic block box to do what it does. If what we do is both make sure we have the features, and this is where the title of the talk, automatic feature engineering, comes in, then even fairly simple features, but just making sure that they're exhaustive and that you cut up all the simple options and that you have a report which looks at the key drivers, and you look for the telltale signs, the perfect predictors, the unrealistically good ones, which will flag out the 100% recall, the 100% precision phenomena, or very close to that, can really help you solve this and help you flag out all the problems which are not actually a feature engineering problem, but a problem setup problem, and you can find these better. So when we have an automatic tool, we exploit them to the fullest. We see the pattern, and we know we have an issue, and we can iterate rapidly and focus on what's really interesting to us. Obviously, I have an agenda. I kept it briefly, so we're recording, and we have a very cool challenge, in case you didn't try it yet. And we're looking for all types of activities. Do I have time for questions? Yes, questions? Yes.
Automatic process that you're doing to check for the features?
Well, you can drop by our booth, but we have a platform which takes the raw data and looks for patterns automatically in order to find stuff. Specifically, all of the examples which were in my slide were stuff which were discovered in a very clear fashion by our platform. And for more information than that, drop by our booth.